catch-up problems in 1D kinematics. These problems often confuse students as they're a little bit more tedious than your regular plug and chug 1D kinematics problems. And although I don't like saying this for a lot of types of physics questions, I can safely say there is a key or kind of trick to making these problems a lot easier to solve, and that is setting their times equal or setting their distances equal. And let me give a quick example of what I mean by that. Let's say we have a car with some certain acceleration and a person running with some certain velocity, and we know that they're going to meet up right here. We don't know at what point they meet up. We don't know the exact time, and we don't know the exact distance. We don't know either of these. But what we do know is that they're going to reach here at the same time, and at the same distance, right? Think about it. Let's say they both start from rest. This car might be here when the person is here, but they're going to end up meeting right here, meaning the total distance they traveled is the same, and they're both in order for them to meet, the same amount of time has to have gone by for them to meet here. Because if they both start at, for example, t equals 0 seconds, they're going to have to reach here at the same time, right? So they're going to have traveled the same amount of time for the same amount of time as well. These are best to do with some examples, so let's go ahead and try a practice example really quick. Kalen is late for his class and needs a ride. His dad, Sachin, is pulling out of the driveway. Sachin, his father, is leaving the driveway at a constant speed of 2 meters per second. If Kalen, starting from rest, can accelerate at 1 meter per second squared, when does he get to his dad? So let's sketch this out, right? So we know that the dad, Sachin, is right here and Kalen, the son, is over here. So we know that the car is going to be moving at 2 meters per second constantly, and we know that Kalen's going to be accelerating at 1 meter per second squared, okay? And let's just write out what variables we have. So for the dad, we have v1, or you know what? We also need to sketch out that we know that they're going to meet up at this point here. We don't know what it is, let's just call it x, but we know they're going to meet right here, okay? Now let's write out what we know. So for the dad, we have v1, and that's about it. And for Kalen, we know that since he's starting from rest, he is going to have a v1, or make sure I write this out, of 0 meters per second, and he's going to have an acceleration of 1 meter per second squared. Don't forget a coordinate system, although since we're moving in one direction, it doesn't really matter. So here we have, these are the variables we have, and now we're like, okay, this is kind of weird, because for constant velocity, we're going to use v equals d over t, and for this, we're going to use one of the kinematic equations, but we're missing a variable for each one. Let's take out our equations, right? And let's really analyze what we have going on here. Remember what I said about relating the times or distances, right? We know that they're going to get here at the same time. So let's write an equation for the dad. The dad is going to have an equation of 2 meters per second, per second is equal to d over t. And for Kalen, we need 2 more equations that we're going to solve with. And since we have to relate time and distance, let's just use time and distance. Why not? We don't know either one, but let's just see what's going to happen. So we know, using our big 5 equations, that's going to be the equation delta d is equal to v1 t plus 1/2 at squared. We know v1 is 0, so that goes to 0. So we're going to have d is equal to 1/2, his a is just 1, at t squared. So these are our 2 equations. Now, let's take a moment and look at it. We know that the distance each of them is going to travel is the same. So this d and this d are equal. We also know they're going to take the same amount of time to get here. So we know that this t and this t are equal. So we just have 2 equations, 2 variables. Let's just set them equal to each other. We know this equation, if we multiply both sides by t, we get 2t is equal to d. And here we also have 1/2 t squared is equal to d. So let's just set the d is equal to each other. So now we have 2t is equal to 1/2 t squared. Divide both sides by t, multiply both sides by 2. Now we have t is equal to 4. So we now know that they are going to meet at 4 seconds. So now let's go ahead and look at a little bit more of a difficult problem. Kalen, now leaving his class, misses his dad and chases Sachin out of the school with an initial speed of 1 meter per second, accelerating at 1.2 meters per second squared. If Sachin is 10 meters away and is walking at 1.5 meters per second, when does Kalen catch up to his dad? Okay, so let's sketch this out. So we know that Sachin is 10 meters away. So we can draw him 10, let's just write dad and son. We know that the distance between the two is 10 meters because he starts 10 meters away. And we know that Kalen is starting at 1 meter per second with an acceleration of 1.2 meters per second squared. And the dad is going at 1.5 meters per second. And we know that they're going to meet up here. Now hold up. How can we can relate their times, right? Because they're both going to start at the same time and they're going to get here at the same time. But are they going to travel the same distance? Because let's think about it. The dad is going to travel only this much, where the son has to travel this much. So let's just label these distances and come back to it later, right? So let's write distance dad. And here, let's write distance son, just to come back later. So we know for the dad that we're going to have a velocity of 1.5 meters per second and a distance of d dad. So we know we can use the constant velocity formula. So we're going to have 1.5 equals d dad over t. And for the son, we're going to have an initial velocity of 1 meter per second, an acceleration, let me just make these all vectors, right? Acceleration of 1.2 meters per second squared. And he's going to travel a distance of d son. And he's going to have some time it takes him to travel, right? Let's pull out our equations and let's take a look at which equation we could use. Again, we're going to go ahead and use the same equation. So we can write d is equal to v1, and we know his v1 is just 1, so we can write t plus 1/2 at squared. We know a is just 1.2, so we could sub that in, t squared, and we know that the d is the d of the son, right? So now we have three equations. We have three variables and two equations. What's going on here? Hold on a second. We can relate their distances to each other, right? Because let's just call it like this. Let's say that this is the distance of the dad, as we know. All this means is that the son is going to have to travel the distance that the dad travels plus 10 extra meters, right? And so evidently these two are equal. So that means the distance of the son is just equal to 10 plus 10 meters plus the distance of the dad, right? So here we can just sub in 10 plus distance of the dad is equal to t plus 1/2, or we can honestly just simplify that to 0.6 t squared. Now look what we have here. We have two equations, two variables again. Let's go ahead and isolate for d dad in both equations. So here we're going to have d dad is equal to 1.5 t. And here we are going to have d dad is equal to 0.6 t squared plus t minus 10. And so we can set these two equal to each other. And we are going to get 1.5 t is equal to 0.6 t squared plus t minus 10, giving us this quadratic where we have 0.6 t squared minus 0.5 t minus 10 equals 0. So now we're left with a quadratic equation. So obviously, what are our steps here? we can just plug this in to the quadratic equation, and that should provide us with an answer of t is equal to negative 3.68, or t is equal to 4.52. And we know that obviously it's not going to be a negative time, so we know that they're going to meet up at a time of 4.52 seconds.